Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have David Rubin with us today. Hello, David.
Hey, how's it going?
I'm doing awesome on this July 7th, 2025, as we record this. I'm in Phoenix, and we are definitely in our summer. So we are hitting the 110s or thereabouts Fahrenheit, 40 something C, somewhere around there, something like that. So yeah, we're cooking. And David, how about you? What's your geolocation?
I'm in Kaneohe, here in Hawaii. Um, it's beautiful here, high
Of
high
course.
70s, the sun's out.
Oh, that's awesome. That's so awesome. Very good. Do you surf? Let me just
Oh
ask.
no,
No? Okay. Just thought I'd throw that in
unfortunately
there since
not.
Hawaii, surfing. Very cool. Very cool. Let me ask, how long have you been in Hawaii?
6 years now.
6 years. Very cool. Very
Yeah.
nice. And what's your position there at Manoa?
I'm a professor at the University of Hawaii.
Very cool. Very nice. And David, what do you like to do for research?
Well, I use Type 1a supernovae to learn about the expansion history of the universe. So, with that expansion history, we can measure the age, the composition, the fate, and yeah, just get a sense of what's going on.
On the cosmology. Very cool. Very nice. Good. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Union through Unity. Cosmology with 2000 SNe using a unified Bayesian framework. And David, take us away.
Thanks. So first, I'd like to give a shout out to my co-authors. So this is work that grew out of the Supernova Cosmology project.
Mhm.
So I've been doing Union compilations since I was a grad student,
Okay.
and each one's had more supernovae, better constraints. And then about 10 years ago now, I started thinking more about the statistics of
Yeah.
type 1a cosmology.
Yes.
So most people think of type 1a cosmology as a series of steps. You take a supernova light curve. So you're watching this supernova get brighter and then fainter. You measure its light curve shape or its decline rate.
Yes.
You standardize, you measure it in different uh, band passes, you get a color, you standardize, you
Yes.
have to correct for the fact that you don't observe every type 1a supernova in the universe. You only observe the brighter ones, the ones that we can see. And
Hmm.
you have to correct for some other things too.
Yep.
And so about 10 years ago, I started thinking more seriously about that. And so I came up with this tortured acronym, the Unified Nonlinear Inference for Type 1a Cosmology Framework, Unity.
Yeah, very nice. Yeah.
And yeah, so this is updating Unity for well, to make it more accurate.
Yeah. More
And
process.
then, oh, sorry.
Go ahead.
Oh, and then updating Union with uh, all of the published supernovae that had come out since I had last done a Union compilation.
Cool.
And so it puts those two together, this updated Bayesian cosmology framework and updated data sets. And uh, we got something a little unexpected out of it,
Okay.
actually.
Cool. Good.
So for, roughly the last 25 years, uh, different supernova analyses have been measuring the parameters for our concordance cosmological model,
Yes.
lambda, cold dark matter,
Yes.
more and more accurately, but not really showing anything new.
Okay. Sure.
And what we found is that we see weak evidence. I mean, it's interesting, but certainly not conclusive
Right.
The evidence has since gotten significantly stronger thanks to the recent DESI results
Right.
and the results from the Dark Energy Survey supernova program.
Uh-huh.
So all of these are finding something fairly consistent, and they're finding evidence that the equation of state parameter for dark energy was more negative in the past than it is today.
Today. Yes.
So instead of a constant equation of state parameter, um, we're finding one that's changing with time.
It's evolved,
Um,
perhaps.
yeah, and so that's very strange. And so this is showing,
Yep.
you know, the weak constraints. It's an old combined with an older set of baryon acoustic oscillation measurements from
Yeah.
SDSS,
Mhm.
not from DESI, but yeah, the result sharpens up quite a bit with DESI.
Nice.
So. Yeah, so it's very strange and it's a bit of a puzzle. And so
Yeah.
we look forward to seeing where all of this goes next. I mean, either the
Yeah.
result will continue to strengthen with the additional data that will be brought to bear on this, or
Come to that.
yeah. Yeah, so let me tell you about the paper.
Okay. Cool. Where would you like to start? Want to do an intro?
Yeah, let's so the intro is sort of hopefully a gentle introduction to supernova cosmology.
Uh-huh.
So it sort of covers everything you have to do. So you have to put together ideally even a couple of dozen different supernova data sets
Mm-hmm.
in order to get the best constraints possible because there's no one survey that's measured enough supernovae over a broad enough distance range to get you really, really strong cosmological constraints.
Mm-hmm.
So you have to think about the union part of things. You have to think about putting all of these supernovae together.
Which is a can of worms, given all the
Yes.
differences between them, right? 0 points and everything else. Yeah.
Yep. So you can see we're already even in paragraph 2 of the intro, we're already talking about calibration paths.
Yep.
So that gives you a sense of how much work it all was. Um, so then we fit everything using a, a model for supernova light curve shape that was new at the time, the latest, then latest SALT 3 model.
Uh-huh. Yep.
And then yeah, we think about standardization. And so the real advantage of Unity here is that it treats standardization as a regression problem. So you're regressing on light curve shape, on color, on properties of the host galaxy,
Right.
and you're trying to predict your observed measurements. And so in some sense, that's I mean, there are always details that you can improve, but philosophically, that's the best you can do. If
Yeah.
you're predicting your measurements with a model, then your uncertainties are going to be maybe not completely accurate because maybe your model, there could be funny business in the model, but your
Sure.
uncertainties are going to be as accurate as possible and,
Uh-huh.
uh, you know, as small as possible in some sense.
Great. I'm with you.
Um,
I'm with you. Mhm.
So let's go on. Let's see what we got.
So just word to the wise, this is a long paper, people, 54 pages. So we will move through. Yep.
um, right. So this is just sort of motivating the Bayesian approach. It turns out that some regression problems are way easier to solve with Bayesian models
Mm-hmm.
than with frequentist models. It's just sort of a funny quirk. Some problems you can always approach with both, but this one really, really, it's much easier to approach with a Bayesian analysis.
Cool. Yeah.
Um,
Unity. Go.
yep, not the worst acronym in astronomy, but
Oh
it's
no, no, not at all. It might be a little, contorted a little bit, but it's not the worst one by any better means.
And it really it fits what it's trying to do very well because it is
Yeah,
trying to unify all of these effects into one um, Bayesian analysis.
correct. Good. Okay, cool.
Okay, so then we have, the outline of the paper there. This is
Oh, here we go.
discussing, yeah, the paragraph we just went
Uh-huh.
by. That was
Yeah, yeah.
discussing the history of Bayesian versus frequentist cosmology analyses for supernovae, and they don't always agree. And then when they
Oop,
don't agree, you have to try to figure out what happened.
here.
Yeah.
Yep.
So let's see. Let's get into the meat of the paper.
And we add in all the other constraints, BA,
Yeah.
BBN, etc.
Yeah, so you can't get a very strong constraint on what dark energy is doing just from supernovae alone. So you
Right.
have to consider the cosmic microwave background and baryon acoustic oscillations.
Hmm.
And if you want baryon acoustic oscillations to be independent of the cosmic microwave background, just as a cross check,
Right.
then you can take Big Bang nucleosynthesis constraints on the baryon density and
Yes. Yes.
yeah.
Cool.
Um,
Very
so
cool.
there's a whole lot of details that
Yeah,
we're
it
just not,
all
yeah.
wraps up many things. It's very cool.
Um, so let's see. Probably more detail than most readers will be interested in, but this is sort of a nice review of what it takes to put disparate surveys together on the same magnitude scale. So if you
Right.
don't get them on the same magnitude scale, if
Mm.
one survey would say that supernova is 16th magnitude and another one would say, well, no, it's 16.02,
And you're
then yeah, that's a systematic error. So that would go into about a 1% systematic on distance.
yes.
So yeah, so it's a pain and there are lots of things to watch out for and you have to there's some unfortunate judgment in this, and it's hard to know for a lot of these surveys whether or not they watched out for everything that they needed to.
Hard to say.
Yeah. So uh, one of the things that we're really looking forward to as a community is getting rid of some of the old surveys and replacing them with some of the newer, better understood surveys like the Vera Rubin Observatory or the Nancy Grace Roman Space Telescope,
Yep.
and trying to get the number of surveys you have to understand down and just be able to understand those newer surveys in a lot more detail.
Get a handle on those systematics. Hmm.
Yep. So,
Hmm.
so there's a whole lot of technical detail here, but
Yep.
we'll skip over that. We calibrate to standard stars. We have to, take some measurements or estimates of passband uncertainties, and we have to, yeah. So unfortunately, most telescopes don't have measured passbands where you're going all the way through the telescope to see what its sensitivity is as a function of wavelength.
Yes.
So you have to sort of calculate all of that after the fact using observations of stars of different colors. And it's a little imprecise, but
It's the best we can do right now.
yeah, it's what we can do right now.
Hmm.
So this table, the first table is a set of shifts. So we're just moving the filters around in wavelength to
Got it.
try to yeah, to try to get different stars of with different spectral energy distributions to line up.
Right.
But
Cool.
some of the shifts are pretty small, some of them are not very small.
Yikes. Yeah. Ooh,
Yeah.
73. Ooh, 180.
Yeah, 180. So yeah, that detector was probably a lot less sensitive in the red than they thought it was. Um, and yeah, some of them are just huge. There's a 124 angstrom shift for the V band. So
Yeah.
that's a few percent shift.
Oh,
I mean, that shouldn't happen, but somehow it did.
but here we are. Okay.
Um,
Pretty wild.
Yep.
And we got
Um,
table, got the Whompers here, a couple of 228s, the winner.
yeah, the I bands seem to be particularly bad. So in general, those CCDs are probably just not as red sensitive as
That is
people
a
thought.
want them to
Yeah.
be, right?
On the plus side, if you measure your pass bands, things look great. So the SWOPE telescope here, the Carnegie Supernova Project folks measured the pass bands, and so we
Nice.
find, yeah, pretty small shifts for them.
Good.
So
Very good.
so that's encouraging that, it's possible to do things right.
Yes. Good. Great. Ooh,
Okay. So let's see. Then there's a discussion of photometry, what data we're including. So we include 2 dozen data sets.
nice. Okay.
Uh, yeah, there's
Okay.
yeah, we can keep going, I think. I'll try to go through the data sets pretty quickly. So if they're your favorite data sets represented, hopefully.
Mm-hmm.
And if not, this section tells you why not.
Good.
Figure one is just
Yeah.
yeah, sort of a technical figure showing some of the really old data sets don't even quote
Oh,
the
wow.
actual
Oh, wow.
magnitude.
Yeah.
Yeah, so they quote these linear transformations of their magnitudes to try
Mm-hmm.
to
Mm-hmm.
pretend that their telescope is
Links.
some standard telescope, and that can go wrong at the few percent level for supernovae, although it works mostly okay for stars.
Yeah.
So this is, yeah,
Definitely.
just showing the sort of mismatches you can get.
Mm-hmm. Between stars and SN1A.
Yeah. So,
Different band.
the
Yep.
scale of the problems, few percent
Few percent.
calibration uncertainties.
But
Yeah,
that's what we
it's,
need.
yeah.
Exactly what we need.
Yeah, so I mean, I didn't mention it, but we are trying to make measurements at the few percent level. So,
Yep.
this is definitely not a good thing to do, and we really just include a couple of older surveys
Okay.
where they did it.
Okay.
Um,
Good. Okay.
so then we have a who's who here, just describing what we did for each
Uh,
survey.
yeah, what
We
we
can
got?
go
We
through it
got
pretty
Talon,
quickly.
Talon Tolodo, CFA1.
Yeah.
And I think this table, yeah.
Yeah, so here's a good summary, so we can look
Yep.
at that.
Okay, sorry. I screwed up. Let's try it now.
Okay, so this is a good summary of the different data sets in here. So,
Okay.
um,
Mm-hmm. Mm-hmm.
yep. One of the nice things about Unity is that it will marginalize with a nuisance parameter over the selection efficiency of the survey. So we have
Nice.
priors, but then we let Unity figure out posteriors.
Mm-hmm. Yep.
So that's those depth columns there.
Yep.
So yeah, you can take very heterogeneous supernova compilation in some sense, and then do, a key step, which is trying to figure out what your selection efficiency was almost automatically,
Nice.
as long as you have a basic estimate of how efficient the survey was.
Cool. Very
Um,
cool. And yes, and some of all these gives 2000 supernovae.
Yeah. So there's another table, I think it might be table 3, that shows the supernovae passing selection cuts.
Okay, let me straighten myself out here.
Oh, we can just go to the table
Yeah,
that
yeah.
the
I just had a rotated table there. Okay.
let's see.
And then we get the Union 3 compilation, phase cuts, final quality cuts, figure two.
Yeah, so
Table three. There we
here's
go.
here's a nice summary. So we collected data for 2,700 supernovae,
Nice.
sort of nicely split actually between low redshift and high redshift.
Mm,
Um,
right.
Then we apply a series of cuts. So we do a whole set of testing with well-measured supernovae to make sure that Sol 3 can consistently measure a distance, if you have data that start or stop on a certain date. So you can take really, really well measured supernovae where the data start early and go late, and then you can
Cool.
cut out ranges of the data, and you can see, well, would I still get a consistent answer? And
Yes.
so the data, enough data cut, um, I actually that might be an even more basic cut, but the phase range cut, for example, that eliminates looks like 8% of the sample.
Mm-hmm.
That one's based on that, and then some other
Nice. Okay.
sort of basic cuts. I guess it's actually a little more than 8% because converged light curve fits. The light curve fits don't converge. That almost certainly means it's either a weirdo supernova with very strange light curves,
Right.
or the phase range isn't good enough for the light curve fit to converge.
You get in there. Okay. I'm with you. Hmm.
So in the end, we have 2087 supernovae. Um,
Cool.
Selected, yeah, like that. Let's go to figure two. I'll show you a different validation test.
Okay.
So, this is sort of the flip side of the phase testing. This figure is asking the question, well, as I go up in redshift, if
Okay.
I have a single survey and I
Okay.
go up in redshift, so I'm going to greater and greater distances, my
Uh-huh.
supernovae are getting more and more redshifted, and
Yeah.
so I'm not measuring the same rest frame wavelength range anymore.
Right.
And so, what these figures are getting at is whether or not I can make that measurement consistent.
Consistent. Yes. Okay.
So, we have supernovae that have been observed at lots of rest frame wavelength range, lots of basically many bands, at least four, but uh, for the SWOPE supernovae, more than that.
Yes.
And then you can knock out some of the bands and see if you get a consistent supernova distance.
Yes.
So, for example, this plot here is looking at, let's say the left panel is looking at, if I
Hmm.
just had rest frame U and B, would I get a consistent supernova distance on average compared with if I have rest frame UBVR?
For
So
four.
like
Yep. Yep.
four bands.
Uh-huh.
And it's pretty good. It might be pulled down a little bit.
Hmm. Yeah.
It's
Very
but it's pretty good. And so if
okay.
you yeah, I mean it's sort of consistent, certainly within 2 sigma.
Yes.
Um and so the right panel converts that to sort of how many magnitudes miscalibrated you might be. And so that is actually taking into account in terms of systematic in the analysis.
Yes.
Um,
And
so
it's
yeah,
you
but
been
we see pretty good consistency between different surveys.
okay. I
So
will
there's
put both up.
no
Yes.
obvious problem there. And of course, this will become a much more sensitive test when we have much more data, which is, I think,
4,000.
going to be a consistent theme here is if we're going
Hmm.
to have hundreds of thousands of supernovae from the Rubin Observatory and tens of thousands from Roman.
Yep.
And so just all of this is sort of a prototype in some sense of what we really want to do.
Pipeline. It's a forthcoming pipeline.
Yeah.
Very cool. I'm with you. Good.
So let's see. Let's keep going.
Okay. Let's see. I'm doing that. Must have missed one. Okay. And then we get into Unity.
Yeah. So,
Let's
well, let's see.
see.
Let's look at the figure first. So there's another consistency check that we do, and it doesn't look perfect in some sense. So for a lot of nearby supernovae, there's actually more than one survey that has measured that nearby supernova. And so the test that we're doing is we're taking what we think is the right calibration, we think,
Then,
and looking at the consistency. So like that left panel
yes.
looks at the whether you get consistent magnitudes out for
Mhm.
different surveys. And
Uh-huh.
the answer is no.
No, but that's not unexpected either.
Yeah. But thankfully, it's basically consistent within the systematics that we're assuming.
Okay,
Um,
cool.
so there'll be another plot of that farther down, but that's
Mhm.
another, having
Okay,
more data than you really need so that you can do subset analyses is a powerful technique in astronomy, and we're using it here to, to the extent that we can.
very cool.
Um, okay, so now I can talk about Unity.
Okay, so let's talk about the new Unity.
Okay, so yeah, Bayesian hierarchical model. The idea is to build a generative model. So you're trying to predict the light curve, the observed light curve. So that's the observed magnitude, light curve shape, and color
Yes.
from the light curve fits
Hmm.
as a function of redshift, as a function of host galaxy properties.
Hmm.
Um, so let's see. We can stare at figure 4 for a second just to acknowledge it. Um,
Oh, wow. Very cool. Okay.
yeah, so this I don't know, conspiracy theory board with string and thumbtacks describes conditional probabilities in the Unity model and then which parameters are included.
Okay.
So in the
Uh-huh.
center there
Uh-huh.
are the observations. So you have light curve shape, you have magnitude, you have color.
Yes.
Um, and so everything is feeding into those. So
Boom,
there is a,
boom, boom. Yep.
yeah, so there's a true latent light curve shape magnitude. And then we actually fit for two colors per supernova.
Right.
Sort of one that's more Gaussian-like, and it's an empirical model, but maybe you would interpret that Gaussian as being a little bit more like supernova intrinsic color due to differences in supernova explosions.
Right.
And
Right.
then there's an extrinsic one, this color red, that's distributed as an exponential. So you might call that dust extinction.
Exactly.
But empirically, this is a, that's sort of a motivation, but Unity is an empirical model.
Fine. Okay.
Um, then so you actually have more fit parameters than observations in some sense. But that's totally fine to do in a Bayesian model if you do it in the right way. You can even, in some sense, have an infinite number of fit parameters
Hmm.
for a finite number of observations. Um, and then, so, going around, you have the green circles describe populations as a function of redshift, as a function of host galaxy properties.
Yes.
Orange is a bunch of global parameters, the standardization relations,
Okay.
um, cosmology, the outlier population, because, once in a while a non-1A sneaks in or something.
Uh-oh.
Um, uh, we have systematics in red. And then we have on the right in blue, we have the selection effect model. So this is
Hmm.
actually, instead of a Gaussian likelihood, you now have a modified likelihood that takes into account not just the supernova you observed, but the supernova you didn't observe.
Ooh,
So that's a
right.
very fun thing that you can do.
Okay.
And then the unexplained dispersion, which is some combination of supernova physics and errors that in the photometry that different groups have made.
Right.
But it's an unexplained dispersion. There's no perfect standard candle in the universe. All of them, Cepheid, supernovae, they
Exactly.
all have they
Sure.
all have some unexplained dispersion. So you can model all of that. Um,
As a lump
so
total.
yeah,
Very cool.
that's
I love it. String and circles.
yeah. It's the rantings of a crazy person, but seems to work.
Not so crazy. Okay. So we got our
Um,
data, we got our tool, Unity 1.5.
we have a standardization equation, so we actually have like two different color standardization parameters for the dust for
Hmm.
that exponential, depending on the mass of the stellar mass of the host galaxy.
Right.
And you do see that they're different. So, it is the sort of thing you have to model.
Yep. And
Let's keep going.
like curves, and we get into
Yeah, we have
periodization.
host galaxy correlations.
Okay.
We can remark on that a little bit.
Okay.
So the idea is for about 15 years now, we've been including host galaxy stellar mass in standardization of type 1a supernovae.
Yes.
The supernova can't know what mass galaxy it went off in, so that's masking some other physics correlation. And a plausible one is that it has to do with supernova age, either something about the
Okay.
age of the galaxy, like, how much dust it has, or something about the supernova itself, like you have different progenitor systems as a function of time, and they have different absolute luminosities.
Yes.
So we don't really know how to treat that exactly. So the idea behind this is something that Unity does is it marginalizes over whether you have a constant host galaxy correlation as a function of redshift or
Okay.
whether it decreases. Because you could imagine at high redshift, all the galaxies are young.
Right.
Um,
Uh,
so you should maybe let those correlations go towards zero. And so
okay.
Unity is sort of saying, well, I don't know if it's going to be constant or maybe it changes with redshift. And so that's just going to be a nuisance parameter for me.
Integrate over. Okay.
Yep. So
Good.
let's see. We've got
Uh, we got
supernova, light curve shape and color population. So yeah, if you need a model for what you didn't observe, then you need to have some idea of how supernovae are distributed in light curve shape and color.
yes.
Um, and so this is the model we're using, Gaussian convolved with exponential, but it's not a perfect model, but it's pretty good.
Okay.
Um,
Improvement, I gather, over the Steve model.
Yeah. And then this figure is showing those Gaussian and exponential parameters as a function of redshift compared. So those are the points with error bars. And then we're comparing against a model that has constant populations with redshift. So that's the
Got it.
filled region. There's not a lot of evidence for evolution with redshift.
Okay.
And it turns out that both of these models give the same cosmological parameters almost exactly. So that's just perfect.
I got
We we we
fine.
let we let it change with redshift, but we don't see that impacting the cosmology. So
Okay.
that's
That's nice.
that's what you want to see.
That's
Yeah.
nice. Good. Good.
Um, so yeah, let's keep going.
And cross checks. Then we get into
Okay, cross checks.
yes.
So here's one where we are trying to see if we get consistent absolute magnitude as a function of redshift out of the different supernova samples. And it
Ah.
within uncertainty. So this one actually does include systematics.
Okay.
Um, and so that's the left panel. And so it looks like we have pretty good consistency.
Yeah.
Um, n- you know, Most samples agree within one sigma, but not all of them. All of them would be weird, but none of them are too far off. So it looks like we're doing some kind of reasonable job estimating the size of the systematics.
Yeah.
Um,
Okay. Uh,
And then the right panel shows that unexplained dispersion for each sample.
oh yes, that
You,
was
you,
in the lower left of the string plot.
yeah, so you will note that some
Ah.
data sets have way higher unexplained dispersion than others. So
Mhm.
they are almost certainly not estimating their uncertainties correctly.
Okay.
Um, Something else that's interesting on here is
Let's look over.
um, some of the data sets seem to do better,
Hmm.
and it tends to be the data sets that do uh, what we think is a more careful job with the photometry. So instead of the classical procedure of I have a reference with no supernova, I have an image with a supernova, I just subtract them.
There you go.
Um, they're sort of building their own generative model where you build a model of the host galaxy light and the supernova and you fit it
Yeah, yeah,
to
yeah.
all
Oh,
the
that's
data.
interesting. Oh, I like that. Uh-huh.
Yeah, so it's sort of, I don't know, philosophically something I like, and maybe it gives smaller unexplained dispersion,
Yeah.
which tells you that some of the unexplained dispersion could be people not doing their photometry correctly and
Okay.
getting the uncertainties wrong.
Okay. Okay.
Um,
Nice plot. I'm with you.
yeah, so it's just fun to see this stuff. And for some of the data sets that look really bad, it might be interesting to go back to the images and try to redo the
Try to
photometry.
redo. Yeah.
But we don't do that in this paper. This is all published photometry.
Right. We're not going to correct anybody's work at this point. Okay.
Yeah.
At least
Um, okay, let's keep going. We're getting into the good stuff.
the good stuff. Unexplained dispersion we just covered. Small SN perturbations. Frequentist Hubble diagram. How about that one?
Yeah, so it's just a sanity check, but we just take our measured magnitudes, light curve shape parameters, and colors, and just make a classical frequentist
Mhm.
distance out of them, propagate the uncertainties.
Yep.
And hey, it's pretty eye candy. And doesn't, it's not anything super scientific about staring at one of these, but
Right.
everyone likes to see it.
Everyone likes his plotter, or at least they plotter anyway. So, yeah. Okay. Oops. The wrong way. Okay. Good. All right. I don't know why I got that because I got one. Okay.
Let's,
Let me get into 0 points.
yeah.
Passes.
This is how a lot of the systematic uncertainties in uh, Union 3 plus Unity impact the distances. So you
Okay.
can actually see that there are two different curves plotted here. So first of all, we're plotting,
Ah.
yeah, so we're plotting every
Uh-huh.
supernova, I think, and then you can see two different
Yeah.
curves. So there's the prior and the posterior.
Uh-huh.
So, for example, some of what we took as our prior on how peculiar velocities can impact the redshifts and thus the derived distance at low
Yes.
redshift.
Yes.
Some of that is being solved for by Unity. So the posterior is smaller than the prior. So that's called self-calibration when you think you
Mm-hmm.
have a systematic, but the data says, oh no, I know what that
I know
systematic's
exactly what
doing.
that is. Okay.
So you can see that operates for a number of these.
Yeah. Yeah. Mm-hmm.
Um,
Less so for others, but yes. And then what we got? White dwarf SED model. Okay.
and those diagonal lines show you when we're zooming in. So we tried to keep everything on the same scale, but there's
Cool.
quite a lot of dynamic range.
Yeah.
Um, so these are, yeah, different systematics that directly affect the distances that you'd measure. And
Wow.
yeah,
Wow. Okay. That's pretty good. Oh, they are ordered, largest to smallest. That's
oh,
important.
yes,
That's
yes,
important to measure. Let's
that's
mention that, I
important
think.
information. Yeah. So largest to smallest.
Okay.
Um,
Okay. Okay.
So we still have to work quite a bit on calibration. You can see 0 points are large,
Yeah.
passband uncertainties, all of the calibration terms are still, sort of near the top.
The drive. Hmm.
The intergalactic dust is going to be an interesting one that we'll come back to. This isn't a new systematic. We've included it in other union analyses, but
Yes.
it's starting to be large enough that it actually impacts things. So we're
Good.
going to have to measure the dust between galaxies so that we can make an extinction correction for it,
Correctly.
in the next generation of surveys.
Wow. Wow. Well, that's pretty good. We're beating the errors down to the point where intergalactic dust matters.
Yep.
That's what that tells me. Very cool. Okay. Good. Okay. Then I got a page out of whack up there.
Yeah, let's see.
Calibrations, changes in cal spec.
Yeah, changes in. So it turns out that all of our current photometric calibration in the optical near infrared, our best calibration is tied to white dwarf model atmospheres for DA
Yes.
white dwarfs.
Yep.
And they've changed over time. Not much, but enough that you have to take it into account. So we do. Um,
Mm-hmm. Yes. Okay.
Yeah, so there was a big change in 2020 when they went to non-LTE models for the white
That's
dwarf model atmospheres.
cool.
So
Good.
there's sort of a
Good.
before and after there.
Mm-hmm.
Um,
Mm-hmm.
yep, but it's not an uncertainty that's perfectly well understood or
Understood.
defined. So this is something where lab-based measurements, it's kind of embarrassing, right? That we're working with these. And we've got percent level changes in the white dwarfs, but NIST can measure 10 to the negative 4 optical power accuracy in the lab.
Mm-hmm.
So we need to get that 10 to the negative 4 to the sky.
There we go.
That's future work.
Future, but at least we're heading in the right direction.
Yeah.
And non-LTE. Uh-huh.
Yep. So
Cool.
let's keep
Good.
going. So let's see. We've got trying to approximate the model uncertainty for salt. I'll just
Hand salt.
yeah,
Okay.
yeah.
By 500, so it's like a box car. Okay. Do, 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 do.
So it's an approximation, but we try to take the approximate uncertainty on the actual salt model into account. And so this is sort of a combination of the expected level of uncertainty, which is what you see in this figure, and then the observed level, which is what you see in way back when the figure comparing UB versus
Right.
UBVR in the
Uh-huh.
rest frame. So they basically agree in the size of the uncertainty you'd expect. So that's a pretty encouraging sign, actually. It didn't used to be true. Light curve tr fitter training used to have significantly underestimated uncertainties,
Yep.
but we might be getting out of that era now. So that's a good sign.
Progress. Progress.
So you can just see like it's worth pausing before we get into the cosmology. You can just see how technical all of this is.
Oh yeah, no, it's great.
Um, so it's a little much to go through in detail, but it's you know if
Necessary.
you want to have an answer that's believable, you have to think about this sort of stuff.
Yep. I'm just sliding up here for a second to check something. Right.
Yeah, so that there was that right panel there,
Okay.
which also showed, with uncertainties, but roughly percent level agreement. Oh,
Yeah, I'll get there. Sorry. I had to fix something. There we go.
uh, so we sort of expect percent level agreement for the rest frame U band, and we see it.
Pretty much get that. Very good. Okay. Yes. Approximate. Yes. Good. Approximate you. Okay. Cool. And then we stay down until we start getting that longer red. Okay. I'm good. I'm with you.
Okay, so let's keep going. We're almost getting there.
It's all good. It's all good.
Um,
Peculiar velocities.
Peculiar velocity. So this is just
Eigenvector.
fun. Yeah, we decompose the peculiar velocity covariance into eigenvectors. So that's
Hmm.
just a technical point of how we actually put this into Unity. And it's just fun to look at them. They show different modes in the
Mhm.
universe.
Yes.
Um,
Interesting.
yeah.
Okay. And
Um,
line of sight peculiarity. Okay. Huh. All right.
yeah.
The
So they
almost one. Okay. And we go down to zero. That's fine. Okay.
yeah, so the peculiar velocity start out as an important correlated source of uncertainties between supernovae, and then they decline to where
With
You
red.
know, they're basically independent uncertainties between
Yes.
supernovae.
Okay. Mm-hmm.
Yeah.
Mm-hmm. But I think you're holding off on the discussion of those peculiar velocities till later. Yeah. Another paper.
Yeah. So
Right. This is
there's
a teaser. This is a teaser.
the next figure. So this is actually pretty fun. So every parameter is in the analysis simultaneously. So you can have a peculiar velocity map and not only estimate the peculiar velocities, but estimate the uncertainties. So yeah, you can
Cool.
see these are random draws out of the posterior, and so you can
Uh-huh.
get a sense of what the uncertainties on the peculiar velocities actually look like.
Right. And just for reference, we're going between -4 and 400 kilometers per second. Okay.
Yeah.
Okay. Wow.
Um,
Mm-hmm. Mm-hmm.
so yeah, just sort of fun.
Hmm. Hmm. Okay. We have questions about that, but we'll leave that. Okay. Cool. All right. And let me get into
Then we get to intergalactic extinction, which is yeah, starting to get to be important. So let's yeah,
intergalactic.
intergalactic extinction.
Hmm.
It's
Do, do,
going.
Joshua. Okay. Mr. Peak. Uh-huh.
Yeah.
Mm-hmm. Okay. Very good. 446.
So this isn't yeah, this isn't a new systematic. We've included it in prior union analyses, but it is starting to be a nuisance.
Figure
So
13. Here we go.
yeah, so this is showing our impact of roughly speaking the right size we think the intergalactic dust extinction is. So these are supernovae at different redshifts measured in different filters. So that's rest frame wavelength on
Boom.
the x-axis. So the
Yes.
filters don't all line up because they're all in observer frame wavelength.
Right.
Um, and so you can see what happens is you have dust extinction. You have
Hmm.
more dust extinction in the bluer filters,
Yes.
but the numbers in the legend show that you're not canceling, although you do cancel out some of the extinction, you don't cancel out all of it. So the
Right.
supernovae get redder, but not redder enough to cancel this completely.
Right.
And so that,
It's
you
not
know, is what's,
strictly intergalactic dust. Right.
yeah, so that's left over that you have to take
Right.
as a systematic.
Right. Okay. Boom, bum, bang, boom. I'm good. Okay. Nice. Okay. Then
Okay.
you get into
So yeah, let's
cleansing,
focus
non-type
on the
1A.
figures. Let's see. So selection effects, priors and posteriors.
Okay.
Oh, sorry, go down to the figure.
Oh, okay. Sorry.
Oh no.
Ah, there we go.
Okay, so this is showing priors and posteriors. So the priors are generally based on these uh, fits that we've done, looking at the magnitude where you stop getting more and more supernovae. So as you
Okay.
go
Nice.
fainter and fainter in a survey, you should get more and more supernovae, but that turns over at some point.
Yes.
Um, and so roughly speaking, that's telling you about where the selection limit of the survey is.
Cool. Okay.
And
And
the posteriors are telling you, okay, if you take that as a rough guide,
okay.
how well are you doing
Hmm.
according to Unity? And so you can see for big surveys like the Supernova Legacy Survey and the brick red color
Yep.
at the top, the posterior is very small compared
Okay.
to the prior. So
That's good.
um, the so that is telling you that when you have big surveys, Unity can actually figure out just from the supernova data how efficient the survey is.
Okay.
Um, you can see that generally speaking, the priors and posteriors are near each other. So it tells
Generally,
you that
yeah.
sort of rough guess was about right.
Hmm.
And then for a lot of the smaller samples, the priors are the posteriors, so the data are telling you very little. And
Okay.
so just taking like plus or minus half a magnitude on how efficient that survey might have been, I mean, that's uh, sort of a very conservative thing to do
Right.
in
Right.
terms
'Cause
of,
that's the spread. Yep.
yeah.
Yep. Very good.
So that's a fun sort of plot.
Yeah.
That's our Is that the first result out of Unity, I guess?
Hmm.
Yep.
Cool. Very cool. Okay.
And then,
Frame magnitudes and validation.
so uh, sort of a great question about all of this is how do we know it works? How do we know that Unity works? Um, and so we did a couple of types of validation for this. So we started off with simulated data testing.
Okay.
So we simulated three different data sets: low redshift, mid redshift, high redshift, 100 different times.
Mm-hmm.
Um,
SN.
and so yeah, so this was a big simulation job. This was a lot of CPU time, but so yeah, this section describes the details of what we simulated. So we simulated light curves. We simulated like a simulated observer where the
Hmm.
observer would like go around and find bright supernovae
Okay.
to spectroscopically observe. So this is sort of a real selection function.
Right. Cool.
Um, and
Hmm.
it's at least qualitatively similar to the actual data.
Data, yeah.
And so then we looked at the summary statistics over those 100. So those are the
Okay.
tables, the one just up,
And
this one. So here we're trying to recover the equation of state parameter and its
ooh.
variation with time. So that's W naught, the equation of state parameter today,
Uh-huh.
and WA, variation with time.
Yep.
So there are a lot of numbers in this table, but it's working pretty well. So
Okay.
um,
Cool. Good.
that's the short summary. There's a small amount of bias that seems to be actually in the light curve fitting stage, not in Unity itself.
Okay.
Uh, but overall, things look great. So that's actually discussed a little bit more in one of the appendices, but that's really getting into the weeds there. But on the whole, things look pretty good.
Good.
Um, so let's see what we've got.
Let's see. So we got, okay, so we got our validation. We recover pretty much what we put in. So it seems to be working. And then mid-Z only. Hmm.
Yeah, so this was sort of a stress test. So normally in supernova cosmology, you try to use as broad a redshift range as you can,
Yes.
get the best constraints possible. But here we took just the mid redshift supernova set out of those 100
Ah, okay.
and pushed it through to cosmology. So this is like the hardest possible test for a model. I mean, one, because there aren't that many supernovae in it.
Right. You're restricted
Um,
to. Hmm.
but two, because you're comparing the low redshift half, if you think about how you would constrain omega m with a comparatively narrow redshift range, you're basically comparing the low redshift half where you have higher signal to noise, less bias,
Yep.
everything's great, to the high redshift half where everything's falling apart. You're losing signal to noise, rest frame wavelength coverage,
Yeah.
selection
Limited.
effects.
Yes.
Yeah.
Okay. Okay.
And so some of the parameters have started to degrade, especially because this is becoming a small sample with not super Gaussian statistics
Right.
for some of the parameters. But omega m, the cosmology parameter we're trying to recover, looks great. So that's the first two columns are unity, and then we compare it with some other less sophisticated analyses on the right. So you put in omega m.3, and that's what you get out, and that looks
Nice.
great. But this
Good. Okay.
Yeah, this was a tough test, but worked pretty well.
Yeah. Congratulations.
Thanks.
Do that one okay. All righty.
So let's see.
Yeah.
Then I think we've got some figures showing the biases. They're kind of fun to look at. So this is looking at what we simulated and then what actually went into Unity. So um, here's the selection probability falling off as you go fainter for those three samples.
Yes.
Um, you
Cliff.
can see the supernovae we simulated as a function of redshift and then what actually went into the analysis. So Unity's having to model those biases out.
Right.
Um, then in the lower left, that's Hubble residual as a function of redshift. So you can see every sample as you go up in redshift, they're getting brighter and brighter and brighter. They're biased downward away from zero. And
Yeah.
that's the selection efficiency.
Okay. Okay.
Um, and
Mm,
then the lower right panel is the same thing as the lower left, but just with the green, the mid redshift.
yeah, just to clean that up a little bit. Okay. Cool.
So, so those are the biases Unity's seeing, and it's getting the right answer. So
Good.
yeah, so that was good to see. Yep.
So far, so good. It's passing all the tests,
Yep.
or at least reasonably passing the test.
Yeah, reasonably. Um,
Okay.
so then let's see. I think the next one we get to is the predictive posteriors. Oh, sorry, one more out of the simulated data. So this is something, yeah, this is kind of a technical point, but it's kind of impressive that Unity did it at all. So when you talk about unexplained dispersion,
Yeah.
you don't really have a physical model of where that unexplained dispersion could be. So, for example, the unexplained dispersion could be in color, like there could be spectral feature differences that impact the color of the supernova,
Okay.
but maybe not the magnitude so much, or maybe color and magnitude,
Yeah, or both. Okay.
or just magnitude. And so there's a set of nuisance parameters that tell you how much unexplained dispersion is in magnitude versus light curve shape versus color.
Okay.
And, and then each of the 100 simulations has a different, it draws from a random distribution of those.
Okay.
And, and then you try to recover it. And somehow it pretty
Wow.
much works.
Wow.
That is, Unity is actually able to say, okay, that that's not a great constraint, and presumably it would get better if we had more supernovae.
Right.
But
Sure.
but this is something that people think
Wow.
of
Huh.
as just a systematic, but no, it's actually to Unity, it's a parameter that can be measured, not perfectly, not with the number of supernovae we have now,
In this one.
but in the future, you could make a better and better measurement of this. And so,
Oh,
yeah, it's just
that's
kind of encouraging to see that
yeah.
this isn't it's not perfect, but it's not garbage either.
Right. So it's on the
Um,
right track. Very interesting.
yeah.
That's very good.
Yeah, so this is something people really worry about in supernova cosmology is what to do with the unexplained dispersion. And so the short answer is, as we get larger data sets, we'll start to figure that out,
Right.
just as parameters, as part of the model, not as, something you have to worry about.
We're done. I don't know what it is. Right. Okay. Wow.
Yeah, that's
Unity is
fun.
doing very well here.
Yep.
Okay.
Right. So then we get to the next set of
Predict.
validation. So that just tells you, okay, if I simulate some data and I know what I put in, I can get it out. But that still doesn't quite tell you that Unity matches the actual supernova data.
Yes.
So we do predictive posterior checks.
Okay.
So that means we do another set of simulated data, this time conditional on the actual data. So we take
Okay.
the Unity model and then draw simulated data directly from it.
Okay.
And then we try to see how much the real data looks like what we drew.
Okay. Gotcha.
And so there are lots of ways that we can do this. So we show, I think, three or four of them here.
Let's see.
Yeah, so they're big figures.
Um,
Yeah, so here's one.
I'm going to zoom out so we get it all, and we'll zoom in as need be.
So this is showing whether or not in different redshift bins, I think each redshift bin here has about the same number of supernovae.
Okay.
So this is showing whether you can get magnitude, light curve shape, and color correct out of the simulations. Do they look like the data?
Okay.
So the simulation histogram with its uncertainty is in black, and then
Hmm.
the data are in the little colored dots, and the
Yep.
dots are colored by, I think it's, yeah,
Z-score.
number of sigma discrepant
Right.
that particular bin is. So when you see orange, that's bad, and when you see black, that's good.
It's good. I'm with you.
Um, so you can see a few things. First of all, let's say on the magnitude, on the left column, magnitude, a lot of the orange dots seem to be bins with very few supernovae. So
Right.
they are just, okay, maybe there's something slightly weird about how Unity handles the tails of the distribution.
Right.
Um, but,
Yep.
y- you know, a tail is probably not going to wag the whole dog.
There we go. Good.
Um, and then something interesting that you see that's real, the X1 distribution, light curve shape, at the
Yep.
very bottom panel, you can see
Yep.
the data are bimodal, and
Yep.
Unity is not modeling that. And
Right.
we're going to do that in the next version, is make add more parameters so that we can
So
get the bimodality of
could be
X1.
bimodal if it comes out. Okay.
Yeah.
I'm with you.
Um,
Yeah.
So yeah, that's interesting. But on the whole, the chi-squared per degree of freedom for these isn't too bad. And when it is bad, it's generally driven by bins that don't have very many supernovae.
Right.
So this looks pretty good. So this is a function of redshift. You know, you want to see things as a function of redshift because you want to,
Get the
see if you're
evolution.
getting the cosmology, right?
Right.
So then the next one is another something, I don't know, stress test. So
Mhm.
this is bins of probability of selection. So we're simulating from the Unity model.
Yes.
Unity knows how like how efficient each survey was at selection. So Unity can tell you in these simulated data samples what your probability of selecting a supernova was.
Okay.
So like and this is a really, really strong test. So like, you
Five.
know, it's easy when you find all the supernovae. It's easy to make a model of that. So like the top row, all of those supernovae were extremely likely to be found.
Yep.
You can build a model of that. The bottom row are supernovae that had a below 20% chance of being found, and
Yeah.
the Unity model is still doing pretty
Still
well.
doing okay.
Yeah, once again, you can see a little bit of weird things for the bright side of the magnitude
All right.
in the left column, but there are very few supernovae there.
Yes.
So this is, I think, this is a test I've never seen anyone do
I haven't
for
either.
any supernova cosmology paper, and super strong test just to convince you that things are working.
Cool. This should become a standard test in the field.
It should. Um, So let's see. Then I think we have one more of these or two more of these. Yes. Okay. So this is looking at sort of like a Hubble residual, a linear combination of magnitude, shape, and color.
Uh,
Um,
right. Okay.
and so it's
Yeah.
you're checking whether the data look like Unity's predictions. So Unity does some
Okay.
nonlinear color standardization, and even the light curve shape standardization is going to look a little nonlinear because of the uncertainties in light curve shape. So uh, this looks pretty good, I think. So I think these are also equal supernova bins for
Okay.
both the simulation and the data. Um, you can see for the very lowest bin in light curve shape, the leftmost bin in the upper left,
Mm-hmm.
the supernovae are, the real data are too faint. So this is, these are magnitudes, so,
Right. Right.
more negative is brighter. So the data are too
Yes.
faint so that you're seeing that you're under standardizing.
Okay.
So that's probably due to nonlinearity in the light curve
Mm.
shape standardization relation and the Phillips relation.
Mm.
That's,
Yeah.
yeah, not being modeled. So we're going to get that next time too.
Okay.
But that's each of these spins has an equal number of supernovae. So again, that's a small fraction of the sample. So it's
Total.
yeah, it's another tail wagging the dog sort
Okay.
of thing. But probably it is real and we should model it because we can model it. So why
Right.
not?
Very good. All right.
Uh,
Cool. Yes, that's that one.
and then
We get
one
into the
more.
cosmological. Oh, okay,
Oh,
one.
there's one more. This is just same thing we've been looking at, but broken out each data set. So if there were some data set that wasn't being modeled well by Unity or something, you'd see it here. But
Oh, I
things
see. These are each of the. I'm with you. Okay, these are each of the data sets. Uh-huh.
so, but these look pretty good. So yeah, there's not,
Overall, pretty good.
yeah, not perfect, but pretty
Okay, there's
good.
a little bimodality there again.
Yep. So
On
we
the
do need to
bottom.
model that.
Mm-hmm. Bimodality there, bimodality there.
Yep.
Comes up in several of the surveys. Mm-hmm.
Yeah, we think it's like an older mode of supernovae. So we think it is something like supernova age or progenitor time.
Yeah, it's tied to the progenitor itself, whatever that
Yeah.
may be. Okay.
So yeah, let's I think that's everything. Now we can t talk about cosmology.
Okay. Now that we're very confident in what we got with Unity.
Okay.
Okay.
So first we're doing uncertainty analysis. Let's see these tables.
Mm,
Um, so most
yes.
a lot of analyses um, break out, different systematics or maybe different analysis variants or something like that and try to put an uncertainty budget together. This is just basic. It's basically based on the covariance
Yes.
between every single parameter in the analysis
Yes.
and a cosmology parameter.
Yes.
So there's no statistical, systematic distinction. It's just, does that term correlate with the cosmology?
Mm-hmm. Mm,
Um,
right.
and so, yeah, we're looking at omega m on the left and then WA on the right.
Yes.
Um,
274. Yep, that's the biggest one. Okay.
Um, so yeah,
Okay.
so you can dig into this a little bit. So calibration matters, but some other things matter too. Peculiar velocity correlations matter. So that impacts, how well you can anchor the Hubble diagram at the very lowest redshift end.
Yes.
Um, let's see, for WA, this delta Z, that parameter is describing how the host correlation varies with redshift. So that's something that most cosmology analyses ignore, but
Yep.
Unity includes.
Cool.
And it does impact WA a little bit. This intergalactic dust, sort of in the middle for WA, but it's really high for omega M actually. And that's just because strange coincidence in the universe. Um,
Huh.
what we think intergalactic dust looks like as a function of redshift. Now, again, we don't have great measurements of it, but what we think it looks like
Pretty good.
changes supernova distances almost exactly the same way as omega M.
Okay.
So
Degeneracy.
it's not like a big systematic in magnitudes, but it just looks exactly like omega M or almost exactly. So
Okay.
yeah, it's just sort of strange. Um,
It is on. Okay. But this is what we get. Okay.
yep. So, if you're looking towards the future, this is telling you, sort of what we need to do. We need to get more supernovae, especially really well measured ones with photometric systems we understand at low redshift.
Yes.
That'll get you the absolute magnitude. That'll help with peculiar velocities. We're going to get that from ZTF, from the Rubin Observatory.
Yep.
So a lot of these are problems that are being worked on right now. And some are problems that we know we sort of will need to work on, like intergalactic dust for the next generation of surveys.
Yes. Yeah, very interesting. You got some new ones here. Okay.
Yeah.
Very cool.
So, yeah.
Okay. And let's go on. Yeah.
So
Oh, the famous corner plots.
corner plots. Okay, so this is looking at how omega m varies with some of our input parameters. And so anytime you see a correlation in that first column, you know that it's something where, that parameter is contributing to the cosmological uncertainties.
Right.
Um, so these are, yeah, corner plots showing standardization parameters.
Okay.
Um, Something that's interesting, although we could have marked it a little better on this plot, is that
Hmm.
the um,
It goes up on the other side.
oh yeah, the luminosity correlation with host galaxy mass. So that's the second column from the right, delta z equals 0.
Yes.
So that's not super statistically significant. So there's not a super strong evidence, weak evidence, but not super strong
Okay.
that luminosity is directly driven by host galaxy stellar mass.
Okay.
But this delta beta R parameter is extremely statistically significant. 0 is certainly more heavily excluded. So that's this, yeah, that one.
Mm-hmm.
Um,
Mm-hmm.
so that's telling you that something about the magnitude color relation as a function of host galaxy mass is different. This is something that people have seen for about the last 15 years. I think
Yeah.
the Supernova Legacy survey might have been the first to comment on it.
Yeah.
But it doesn't tell you exactly what's different, but it tells you something's different. Probably dust extinction, but we don't know exactly.
Okay.
Um,
Cool.
so let's see. Let's see what else we got. So this is standardization parameters.
Then we got
Right. So this has the unexplained dispersion and how the unexplained dispersion is distributed between magnitude, light curve shape, and color. So that's like the three on the
yeah.
right are fraction in magnitude, fraction in X1, light curve shape, fraction in color.
Mm-hmm.
Um, you can see they don't super correlate with the cosmology, but they do a little bit, and so
A little
it's
bit.
it's sort of good to get everything into the same analysis.
Absolutely. Dotting I's and crossing T's.
Yep.
Okay. So that
So let's
one more
see.
corner, I believe.
One more. The outlier model.
Uh,
It's not a terribly good outlier model, honestly. One of our parameters in this run actually a couple of the parameters hit the bottom limit, and we actually
yeah.
comment on this and change things. It doesn't impact the cosmology too much, but
Yeah.
this is sort of the nominal run. But yeah, not too much correlation with cosmology here, but it's just nice. I mean, this is going by a little fast, but this is actually, if you have data that has outliers,
Yeah.
then
Okay.
building a model that includes both the inliers and the outliers, where any point can probabilistically be an inlier or outlier, rather than sigma clipping or something like that. That
Oh,
can
yeah,
be
yeah.
that can be very powerful. So uh,
No reason to clip.
yeah. Okay, so then the text we're going by is describing the data that we assume, Planck cosmic microwave background, SDSS, BAO, and I think we include 6DF as well.
Let's see.
Um,
It's Gus.
okay, so now we're getting to
BAO.
there were some supernova distances.
Yeah, I'm just winding up. BAO.
Yeah,
BBN.
BAO, BBN.
CMB and H. Okay.
Okay, so we include both main Hubble constant measurements from the local distance ladder, one based on Cepheids from shoes,
Okay.
and one from the Chicago Carnegie program
Okay.
based on tip of the red giant branch.
Yep.
Um, so let's see. Then we've got the supernova distances. So this is showing distance as a function of redshift with respect to flat omega m point 0.3 cosmology. And so you can see something a little odd, which is there's um, so yeah, the two uncertainties
Okay.
are taking correlations into account that would just be degenerate with the absolute magnitude. So it's the lighter color, and then
Mm.
subtracting off the mean, which is not degenerate with absolute magnitude for the darker color.
Okay.
And so what you can see is our best fit omega m is about 0.36, whereas from BAO plus CMB, it's more like 0.31. And so that's not hugely statistically significant. I think it's a little under 2 sigma. Um, but it's
Mhm.
up.
Yeah.
And then the red curve is also a good fit. So that's BAO plus CMB plus supernovae.
Okay.
And that red curve is a time evolving dark energy model.
Okay.
So
Yeah.
it's
Right.
not conclusive, but it's certainly suggestive.
Little hint, little hint.
Little hint, yeah.
That was in the abstract too. Right.
Yep. So that's really what Unity's picking up on is that
Hmm.
little and so you can see, it's not any one redshift bin that's driving the results.
Yeah.
Um, it's
Spread
just
across. Hmm.
yeah,
Which is good if it's real.
yeah, that's encouraging. So we'll see how this continues to evolve.
Ha
No,
ha ha
yeah, no pun intended.
ha. Pun intended there. Okay.
Um, so here's the on the right there. There's a comparison. So
Yep.
Pantheon Plus was another big
Hmm.
compilation, Supernova 1A compilation,
Uh-huh.
and we actually find larger uncertainties than Pantheon Plus.
Okay.
And so we're still working to understand that.
Mhm. Well. Mhm.
Yeah. So our nominal result is the uh, medium blue, light
Blue.
blue,
Yeah,
whatever.
the lighter blue color, yeah.
Lighter blue, and then Pantheon Plus is the brick red there.
Okay.
And
Yeah.
we're still working to figure out what's going on there. Um, but
Okay.
so now what we're doing is trying to run Unity and the Pantheon Plus
Right.
sort of framework on the same simulations.
Exactly.
But our first attempt to do this got basically the same uncertainties on the simulations. So,
Okay.
um,
Mystery.
yeah. So we're still continuing to look. This is an area of active research, trying to figure out what the difference was there.
Cool. Good.
Um,
Mm-hmm. Mm-hmm. Mysteries are good.
so yeah, but it just goes to show you how nice it is to have two analyses, right?
Absolutely.
I mean, whether it you know, irrespective of why it turns out that there's a difference. Just having the confidence that you get from having two
True.
almost completely independent analyses.
Yes.
Yeah.
Yeah.
Um, so let's see. We should be getting into the cosmology figures.
Yeah. Now we're gonna get into the SN constraints.
Oh, table, big
Table,
table.
big table.
So
This one. Okay.
yeah, we have
Oh yeah.
chi-squareds, we have the Hubble constant, omega m, curvature, which sometimes we fix to zero, sometimes we include.
Okay.
The dark energy equation of state parameter W and its time variation with redshift, and the dark energy task force figure of merit, which is
Okay.
the inverse area of the W naught WA contour. So it's It's a measure of how precise you are, and higher numbers are better.
Hmm.
Um, for the next generation of surveys, we should get to 15, 20, maybe even more.
You,
Um,
because now we're down
so yeah, just
factor of 10, right?
yeah,
Basically.
maybe even more.
Yeah.
So
Okay.
we, the mysteries that we're sort of scratching our heads about in the current data, they're either going to go to zero or they're going to go to something highly statistically significant
Okay.
in a few years.
I love that. Awesome.
So, um,
Nice.
and then yeah, you can see we did not take sides. We included both H naught local distance ladder measurements, both of the
Hmm.
really strong ones. So
Hmm.
yeah, they're
Good.
both in there. You can see the chi-squared is
Yeah.
extremely high when you include the Cepheid measurement and the early universe constraints. So that's just telling us that yes, our analysis can show the Hubble tension.
Right. Good. That hasn't gone away. Okay.
No. So let's see. Then we've got some nice eye candy contour plots. So we've got
Oh,
the
yes.
famous one.
That's a famous one.
Yep. Um,
Hmm.
Yep. So you could see how much the BAO contour has improved.
Absolutely. It used to be much bigger.
Um, and now we're working with some high redshift supernovae that will hopefully come out in an update this year,
Cool.
and that will shrink the supernova contour significantly as well.
Cool. Good.
So
Yeah, a little bit of
yep.
good. And so here we got
But
it in omega lambda omega m, and then we got it in W omega m.
W, yeah. So there's the equation of state parameter W.
Mm-hmm.
So there you're actually getting, I think, a better constraint from the supernovae just because they're more perpendicular to the CMB.
Yes.
And then we get the really exciting one, W naught WA, and you can see that lambda CDM, equation of state parameter,
Mm-hmm.
-1 for all time, that is outside the 2 sigma contour.
Yes, it is. Okay.
Yeah. So
Wow.
this is
Wow.
sort of exciting, and it's gone up to depending on which supernova sample you look at, high threes to maybe even low fours sigma with the DESI results.
Yeah.
So
Wow.
yeah, that's pretty exciting, but uh,
Tantalizing hint.
yeah, but we'll either nail it or disconfirm it in a few years. So
Yeah.
we've
Both
got
are
our work
great.
cut out for us. Yeah.
Both are great. Very cool. Oh, and then we end off with a little WAWO, WAWO. Yes. Okay.
Yeah, so this one just shows you that there's no obvious, single data set that's driving you away from Lambda CDM,
Right.
BAO, CMB.
Hmm.
So this is 1 sigma on the left, 2 sigma on the right, so that you
Okay.
can look at whichever contour you like.
Mm-hmm.
At this point, BAO plus CMB with DESI gets you to about 3 sigma tension with Lambda
And this,
CDM.
yeah.
Um, and it's in the same direction. I mean, the thing that's
Okay.
interesting is that,
Okay.
all of these seem to be collapsing around a point. It's just that point is not lambda CDM.
Right. Right.
So
There. Right
either we
there.
got, yeah.
And that's not lambda CDM. Okay. Either in WA or in W.
So either we got very unlucky,
Uh,
which that can happen. There have been statistical fluctuations, I think, some even in high energy physics where really, it's really statistical, you're looking at bin counts
oh,
on
there's
a
famous
histogram.
examples of that. Okay.
Yeah, where, 4 sigma bumps have gone away. So, it's either we got unlucky or we're starting to see evidence of something pretty interesting.
Indeed.
So
Tantalizing. Very cool. Very cool. Okay.
So
Yeah,
I
we
think that's it. Unless you're really interested and you want to see
pretty
a lot of
detailed.
appendices, you know.
There's seven of them. There's seven appendices here, folks.
Yeah, you can see the scroll bar on the right and how we're not at the bottom yet. So,
So we got magnitudes and moduli, parameters and priors, a good definition of the symbols. That's good, like curve shapes, color populations, 0 points,
0 points. Important.
EAO distances,
Yep.
and one more, no, two more, CMB, compression, and variation of light curve fitting. So you'll enjoy all those details. Very,
Yeah. So if you thought the paper wasn't technical enough,
yeah,
it could have been worse.
there you go. There you go. David, I want to thank you so much for walking us through your very awesome article. Thank you so much.
Yeah, thank you.
Yeah, and you touched on it a couple times. So let me just be a little explicit and push on it here a little bit. And where do you think we go from here in the near future? Right, we do have, as you mentioned, we have a couple of new telescopes coming online, which should get us from 2000 to at least double that, if not an order of magnitude or so. Uh,
Oh, at least an order of magnitude. Yeah.
yes, good, good. And so where do you think we go given the new data coming and where the most return is going to come from on a new analysis, you maybe using Unity 2.0 or something like that.
Yeah. So, sort of it's not always when that you're excited to throw away data, but that's given the systematic uncertainties in the current data,
Ah, got it.
that's
Got it.
that's going to be pretty exciting. So, over the next few years, we should get enough supernovae from the Rubin Observatory, from ZTF, from a couple of other nearby supernova programs to basically toss almost all of the old data, at least as far as dark energy is concerned.
Okay. Yep.
So, and we should understand all of those instruments much better. So that's
How
just
important that.
just doing that is going to be a big improvement. The numbers are going to go up by, yeah, at least a factor of 10. So it's just going to be very exciting. So more supernovae, better understood, lower systematics.
Mm-hmm.
And then with any luck, the Roman Space Telescope is going to launch next year. It's coming up, and get us, another 10, 20,000 supernovae at the highest redshift end. So we'll just have better wavelength coverage, redshift coverage, many, many, many factors, more supernovae, and we should understand all of our uncertainties better.
Very cool. Very cool.
Yeah.
It's going to be awesome. Let me ask, when on the peculiar velocity, do you anticipate putting a paper out on that before all these other telescopes come online?
Yes, so a few of us are working on one.
Okay.
So a bit of a technical point, but so our peculiar velocity constraints are coming from the supernovae alone, but you can also learn something looking at how the galaxies that DESI, for
Ah,
example,
mhm.
is measuring on the
Yes.
sky. So those supernovae have to be falling towards overdensities.
Right.
So a simultaneous supernova density, galaxy density analysis would be a very, very natural thing to do. And
Indeed.
we're working towards it, but
Cool.
uh not out yet.
Yeah, no secrets yet, but we will look forward to
Yep.
that. Very cool. Very cool. Well, it'll be really exciting to see this develop over the next couple of years as we finally get some better answers on some of these things. So it's very nice. It'll be really exciting to see.
Yeah.
Cool. David, I want to thank you so much for walking us through your very awesome article.
Oh yeah, thank you. Uh
Yeah. And
uh
go ahead.
oh, I hope everyone enjoyed it.
Oh,
It's a
I
little
enjoyed it.
technical, but you can go through and look at the figures.
There you go. Very cool. And that will do, everyone. And I hope this made your Type 1A Supernovae Cosmology Day just a little bit better. And we will see you on the next one. Bye bye.